Okay, so atomic size. So you guys can remember how to figure out the size of the atom? So let's pull up a periodic table. Everybody has a periodic table available?
Yes.
Yes.
Like 20.
Okay, so let me
6,
pull up my periodic table.
25, 75. Okay. Atomic size.
Okay, can you guys see my periodic table?
No.
You just see the line.
Whiteboard.
How about now?
Yes.
Okay, so okay, so can you identify the atomic numbers, what atoms we're looking at, or elements that we're looking at based upon the atomic number? Yes, no, maybe?
Yes.
Okay, so help me identify things. What are our ones that we're looking at?
So we're looking at calcium.
Calcium. Can you see my purple writing?
Yeah.
Okay.
Is it
Barium,
barium?
Barium,
manganese,
Magnesium.
manganese,
Arsenic.
arsenic,
Nitrogen. Bismuth. And then
uranium.
uranium.
okay? So that's our first start, right? So what do we know about trends? Trends of atomic size.
It increases as you go from right to left on the periodic table.
So it increases when it goes from right to left. So let's draw that. So it increases as we go from right to left. Okay.
Oh,
And
And top to bottom.
and
It increases
concrete.
top to bottom.
It increases as you go from up to down.
from top to bottom.
Yeah, top to bottom.
Increased.
Okay. So who do we expect to be our largest?
Element.
Who?
Is it
Barium.
barium?
Okay. So then who's going to be our next largest?
Calcium?
Calcium.
That
Uranium.
Uranium?
okay, so let's talk why calcium isn't the next largest before we go on. Okay, so have you guys heard of the Russian dolls?
Yes.
Do you guys know what a Russian doll is?
Yes.
Yes.
Everyone? Because I only hear two people talking. If you don't know what a
Yeah.
Russian doll is, if you don't answer me, you are in contempt. I have anger for you, right? You gotta let me know if you know it, if you don't. It's okay if you don't know it, because if I don't know you know it, then I can teach you it, right? If you act like you know it and you don't know it, then that's on you. You're asking for that F, because this is gonna be on the test, okay? You've gotta be passionate about what you're doing. You can't sit there and be a bystander. Be active, okay? Even the baby's being active. The baby says, hell, I don't know what a Russian doll is. You know, if the baby can
I
do
need
it,
the
you
kind
guys
of
should be
coffee
able to
you
do it.
guys have.
Good morning, everybody.
So let me show you what a Russian doll is, because my guess is I'm going to say about a third of you, or maybe a little bit more, don't know what a Russian doll is. And you probably know what it is, but you just not seen it in this context. Like, ignore the circles.
Can you hear me?
I can hear you. Oh Lord, what
Yeah.
happened? You
Thank
fixed
you.
it.
Yeah, something happened. I just reset it. That's it. All right.
Okay, so these are Russian dolls. You guys see those?
Yes.
Yeah.
Okay, so you see how this little doll here, this little doll will fit into the other doll,
Oh,
and then
yeah.
this doll will fit into this doll, and then this doll will fit into this doll, and this doll will fit into that doll, right? So if you
Yes.
look at your
Yes.
periodic table, your periodic table is exactly the same way, right? But instead of dolls, you have your periods, right? So remember, these are your periods. So 7 is your biggest doll, right? And all of the other electrons will fit inside of it in each of those periods. So which of these dolls are bigger? The biggest doll or the smallest doll?
The
big
biggest
one.
one.
The biggest doll is bigger, okay? So that's the same thing, that all of the elements that would be in that table, right? And in row 7 are going to be bigger than the ones in row 6, because it's only defined by that space. Okay? Do you guys see that?
Yeah.
Yes.
So to put it into a graphic detail, I know I'm not drawing the right orbital, but like, so here's my baby doll, right? So then here's the other doll. So between here and here, that's where all of these elements are going to be able to fit into. So the ones that are in the first row, they're only going to be fit into here to the center of the atom. Okay?
Okay.
So and this is the center.
So the 7 is the
That-
biggest one?
What was that?
The 7, number 87 is the biggest one?
So 87 will be the biggest one. So who's going to be my
Yeah.
smallest one?
Number 1, helium?
Helium.
No,
Helium is
hydrogen.
going to be smallest. Okay?
Okay.
Okay, piece of cake.
It's making more sense.
Okay.
I
So,
don't.
okay, so as we go across,
H.
okay, so who's next? Ooh, that's the wrong one. R-E.
Oh, I-E. So
Yep.
H.
Then would it be element number
B-
83?
Is-
Bismuth?
That's right. Okay, somebody other than Ryan. Who's next?
Calcium.
Calcium.
Yeah.
All right. Who's next?
Mn. 25
Okay.
Mn.
Okay, Andy, now you gotta let somebody else answer.
So we
33?
Oh,
Arsenic.
Arsenic. And then the smallest one, oh, I'm having it go the wrong way. Sorry. You guys should have corrected me. Remember, Pac-Man eats the biggest one. And our smallest?
Nitrogen.
Nitrogen. Oops. There you go. Pretty simple, right?
Dr. Henry, I will have
Yes.
a table with this one all the time when I do map. You know, like on the V side, you know,
Yes.
and the picture is this one is the big side and then this one is small one. You know,
The best way of remembering it, right?
the pointy
is-
one is small one and then the large one is the big one.
Did you ever play Pac-Man, Andy?
I play Pac-Man, but you know, Pac-Man, they it like that.
Yeah, look. See, Pac-Man. Pac-Man eats the bigger one. See? Pac-Man. Pac-Man eats the bigger one.
So the mouth is bigger.
That's right. The mouth is going to go to the bigger one. Yeah, so Pac-Man eats the bigger one. That's how I always remember it.
Okay. So the pointy one is small one. Okay.
Yeah, the point is the smaller one.
Okay, I get it.
Okay? Any other
Yeah.
questions?
Yeah, I have a question.
Yeah.
Can you hear me?
Yeah, I can hear you.
Okay. So if atomic radius increases from right to left, I see that for largest to smallest, we're focusing on period 6.
Yep.
Right?
Yep.
So why is it, I guess what I'm saying is so you're saying bismuth is larger than
No.
calcium, or I'm sorry.
Oh, yeah.
Bismuth is larger than Mn?
Yeah, business is larger than calcium and Mn. Because
Well,
also,
why is that if it increases from right to left?
it doesn't, okay, because you're defined by that period, right? So remember when I talked to you about the dolls? Look over here, right? So this is your smallest doll. That's your this is your nucleus. The filled in dot is your nucleus. This is going to be your smallest doll. This is going to be your next largest doll. So when we're talking about those elements, your elements can only fit within here. So period 1 elements are only going to go from here to the nucleus. So they can only fill this space from here to the nucleus. They're limited by that first period. So the ones that are in period 2 can only go from this one to this one. So I'm going to put a little arrow like this. Well, that's kind of impossible. So you can kind of see. So for period 3, so period 3, all of the elements in period 3 are going to be filling this space, right? So if I'm in period 2, anywhere in period 2, I'm going to be smaller than those that are in period 3, because this are the outer rings, right? They define the space where these electrons are going to be sitting. So right here, that first one, from here to here, so that is going to be for period 1. Right? So all of your elements are going to fall in there. So anyone that's in period 1, right? That's your hydrogen, that's your helium. So those electrons only are going to fall into this region. The electrons that are in period 2 are only going to be in this region. The electrons in period 3 are only going to be in this region.
Okay, so we should focus more on the periods as far as because that tells you where the orbitals are?
Yeah, because the periods are energy levels, but they're also defining the space where those electrons that are in that period are going to be located at, right? And so if you look at it,
we should focus more on the periods than the actual groups when it comes to this.
Yes, so periods are going to have priority over groups, right? But you have to look at both. You can't just focus on one or the other, right?
Right.
Because think about it.
Okay.
As you're putting out more and more shells, you're going to get bigger, right? But if you're all in the same period, if you're all in the same period, if we take everything from group 3, right, and compare those to each other, we always know that the ones that are on this side are going to be smaller than the ones that are on this side, because they're all in the same period.
I see.
Okay. So you see it?
I get it
Thank
now.
you.
Yeah.
Just gotta make it good to understand more.
Okay, so we just talked about atomic size. Now let's talk about ionization energy. Oops. Okay, so what is the trend for ionization energy?
Right to left, or
Okay,
excuse me, left to right.
okay, so we are flipping this, right? I can do it. See my skills here. And
It decreases down the group.
okay, the arrow just tells us which way it's increasing, right? So we're saying that hydrogen is going to have a higher ionization energy or a lower ionization energy than francium.
Higher.
Higher, correct?
That is correct. Okay. So based upon our folks here, what is going to be the order? From largest to smallest. Who's going to have the highest ionization energy?
It'd be nitrogen.
Yeah.
Okay. Man.
VA.
Arsenic.
Arsenic, yeah.
There you go.
Okay.
Manganese.
I got MN. Or I'm sorry, BI, not MN.
You got BI.
I got BI.
Okay. So you are correct, actually.
Okay.
Oops, hold on.
Man, it's confused.
So you're going to ask me why, right?
Why?
That's what I'm hoping. All right. Okay, so let's talk about why. Okay, so if we take a look at these guys are very close to being noble gases, right? So if you're really close to reaching your goal in life, are you going to let somebody start taking money away from you or taking what you accomplished away from you? Or are you going to be like, you know, hey, we're going to fight for this, and you're going to put a lot of energy for fighting for it rather than having people take it away? Isn't that true?
Yes.
Okay,
Yeah.
so that's the same thing with these elements. They're really close to reaching their goal in life and being a noble gas. So since they're so close, they're going to fight for it a lot more than any of these guys over here that are pretty far away. You know, they're kind of like, you know, those kids that you hung out with that decided they weren't going to go out and get an education. They're just going to smoke pot on the corner or whatever, you know. You guys, you know exactly what I'm talking about because I have friends like that still, you know. I like hanging out with them when I want to have a good time, but I know they're not going to help me get to where I want to be, right? So are you going to these guys here are kind of like, you know, they don't care about life right now. They're just like, they're happy at the station that they're at. They're cool with that. Where you guys are hungry, you want to get better, you want to be more stable, right? So you're not going to let somebody take away from you. So you're going to fight stronger to get to where you want to be. You're going to fight to pass this class. You're not going to let Dr. Henry get in your way. I'm not going to let that motherfucker stop me from getting my A in this class and getting on to micro, right? You're going to fight for it. You're not going to give it up. So since you're so close, you're not going to quit now, right? Where these guys, they're so far away that they're like, you know, I don't care so much. It can happen either way, you know? If it happens, great. If it doesn't, you know? So do you see what I'm saying?
Yeah.
Yes.
Okay. So these guys are always going to end up being greater than these guys over here, right? Even though, so in this case, it's not going to be the period that matters. It's going to be where they're located at, the group, okay? So group has priority over, okay? And there are going to be some cross points where, you know, and that's always the case. There are always going to be a little bit of cross points. That's going to happen. And then in most cases, this was an extreme case. This is part of the reason why I used such groups that were so far away from each other, right? Okay, so who will be next then?
20.
Would it be manganese?
Manganese, okay. Oops.
Rhenium?
Oops. Coffee's just kicking in now. Okay.
Calcium.
Calcium.
And the bum on the of all your group of friends here?
Barium.
Okay. Piece of cake?
Yes.
So always
Piece of
think about
cookie, like Andy says.
a piece of cookie. Okay, so now I have a question for you. Now that you know this, right? So on the periodic table, who is going to be, has the highest ionization energy, going to be like, hell no, you're not taking away what I've earned. Not at all. You know,
Helium?
you're not taking it. Who is it going to be?
Helium?
Helium.
Wouldn't it
Who-
be 87? No?
No. Why would 87? 87 is a bum. Right? He's so far from, well, you know, even though he can drop, francium can drop an ion, right? But he's dropping an ion. That's the whole purpose of ionization energy, to drop it. He's like, I don't really need it. I'll throw it away, right? So he's kind of like one of those rich kids that just has money to throw around, right? That's francium. He has so many that he's just like, I don't care, right? Where helium already has what he has. He's rich, and he's like, he's one of those kids that were poor the whole life and they became rich, and then now he's rich, and he's like, I am never going to be poor again, so I'm not giving up shit. So we're going to fight for it, right? Where francium is like one of those rich kids that are just like have been rich their entire life and they just have extra excess, and so he's just going to pop it around. So francium is going to be the weakest, right? So francium is like literally, it takes, you look at francium wrong and it drops that electron, you know? Just give him a little glance his way. He's like, okay, here, I'll drop it. You guys heard of, you know, people, have you heard of people who just leave their keys in their car?
What?
Yeah.
Yes.
Okay, so people that typically just always leave their keys in the car, they're wanting their car to be stolen, right? Otherwise, you wouldn't leave your keys in it, right? So that's the way I think of francium. Francium are those type of people that just have so many cars and they're so well-to-do that they'll just leave their keys in the car. They don't care about it. Where somebody who's like, who worked really hard to get that car, and that, you know, they're gonna be like, no, you're not taking my car, right? So you're gonna be less likely to sit there and give it away, right? When you get to that point where you got what you got, you worked hard for it, and this is your first car. This is your baby. You paid for it. Mom and dad didn't pay for it. You're gonna be like, let me shine this up real quick, you know? Let me sit there and make sure that the engine's running. Take care of my baby, right?
That's right.
And then, but if, you know, mom and dad is giving you every car that you've had, and there's about 8 cars up in the yard and everything like that, you're gonna be like, oh, I crashed it. Oh, dad just crashed another car. So that's kind of like what you want to think about in this context of ionization energy, right? Okay, if you worked really hard for it, you know, and you want to maintain that, you're not gonna be willing to give it up freely. So you're gonna put in a lot of energy to keep it. Where things that really don't care, they're gonna want to drop it. These guys, they want to get rid of electrons. All of these guys here, except for hydrogen's kind of weird place, but these guys down here, they want to get rid of electrons. So they're gonna have the lowest amount of ionization energy, because ionization energy is the energy that it takes to remove an electron. These guys, they want to get rid of it because that's how they become like a noble gas, right?
Okay, so if would you say that ionization energy is like the example with the, say you're going to steal a child, right? So
Yes.
is that the same concept with ionization energy?
Yes, exactly. Yes, exactly. Because like these,
So if it's
these
further
here,
to the right with the noble gases, it has, it wants to keep those, but the ones that are further to the left are more susceptible to losing them,
that's
the
right.
electrons.
Yeah.
Okay.
They're like, yeah, these guys are like, oh, that kid is a burden. I don't really want it. They didn't want the kid in the first place and just happen to have it, right? And they'll be like the ones that are dropping it off at a doorstep, you know?
I have another weird question.
Yes.
So like, you know, when we do the electron configuration and we're finding the valence electrons and whatnot,
Yes.
like, is the s orbital always on the same I guess, plane? Like, is it always going to be, like an S will always be in the same spot, or is it the periods that identify how close it is to the nucleus?
The periods are the one that identifies how close to the nucleus. If you go back
Okay,
in
got it.
chapter
I was
11,
thinking, okay.
yeah, there's a figure that actually shows you. And remember when I talked to you about the dolls, right? So
Right.
the dolls, the 1s is that smallest doll. The 2s is the second smallest, and then on forth, right? And so you're just having them built outside of each other, but you're putting it all together. They're all together in the case of, let's say we're talking about cesium, right? So all of those, you have 1s, you have 2s, all of those are present, but those are just capsulated in those smaller dolls. So they're capsulated in those earlier periods. And so it just gets bigger
I see.
and built out from there.
Got it.
So you can't think of them as independent, right? It's just building on each other, okay? Okay, any other questions? Excellent. So this should be easy, the next one. So we have metallic characteristic. What color best represents a metal? Metallic characteristics. So who's going to be the one that has the most metallic characteristic?
Barium?
Barium.
Then
Would it be uranium?
radium or calcium.
Or calcium.
So this one again, we're going to be relying on where they're located at. So we're going to go from their groups. They're going to have priority over their distance. So these guys here are going to have the least metallic characteristics, and then these guys are going to be somewhere in the middle, and these guys are going to have the most.
So calcium next.
Yeah. And then,
Would it be rhenium?
okay. And then,
Manganese?
and then,
Bismuth?
Would it be bismuth? And then would it be arsenic?
and then,
Nitrogen.
Nitrogen?
okay. Now, let me give you a hint here, right? So if you
Argon.
actually take a look,
You put argon instead of arsenic.
oh, sorry. Thank you. Did I do it twice? No, arsenic.
No.
Thank you, thank you. So it's not, okay. So I'm struggling here. So post-transitional metals. So if you look at it, right? Look how far the metals go out in terms of metals in group 6. So it goes all the way out to group 16, right? I'm not at group 6, period 6. It goes out all the way out to group 16 in period 6. Then period 5, it goes out to to group 14. Period 4 and period 3, they both go out to group 13. Okay, so that kind of also helps us understand as we go down, we're getting more and more metal characteristics, and it also seems to go out a little bit further. So you're getting things that are in that other realm that are metallic as a result of the fact that they're getting bigger, right? So those characteristics. So if we continued and we start analyzing these guys right here, right? So if you notice, a lot of these guys are transitional metals, and then these guys don't have anything associated with it. They're in the gray because we don't know about the characteristics of it. We don't have them. They're not stable long enough for us to know. But if we get them stable long enough, what would we assume?
It would be
With these guys.
transitional.
These would be metals. And what about this guy?
Post-transition metal.
Okay. All the way, we'd assume at least to the same point of Po, if not further, right? So at least to group 16. So do you guys see that?
Yes.
Are you there?
Yes.
So can you see that you can make some educated guesses, or some hypotheses about characteristics of other metals, right? Or things that are going to be metals based upon trends. You guys see that?
Yes.
Yeah.
Okay. And so that's also going to be important because that's how you become cutting edge, right? You start thinking about just beyond what we know, right? Because it's great to know what we know, but that's not going to get us to that next level. And you guys are my future, right? And so I want to make sure you guys get to that next level. If you guys are just staying where I'm at, you're doing me no good, right? You want to all you guys want to get to that next level. So you want to know what I know and beyond that. You guys got that?
Yes.
You understand your job? And I realize I misspelled characteristics. I called it trotteristics earlier when I emailed it to you. So that's why I'm not an English major. Okay, any other questions?
I have a question, Dr. Henry.
Yes.
So for ionization and metallic character, the groups have more priority, right?
Yes.
And then for atomic size, the periods have more priority.
Yes.
Okay, thank you.
Dr. Henry, you said the metallic characteristics, the periods are the priority?
No, for metallic characteristics, the groups have priority.
Okay.
Okay.
And then it's also priority for ionization energy.
Yep.
Okay. Thank you.
Dr. Henry,
Yes, Andy.
you know, like, the Ca, calcium is metal, is not noble gas.
Ca, calcium is not a noble gas. All noble gases are here in blue.
Oh, how about on my noble gas is on yellow?
No, on yours, or it's this one right here. It's group 18. Group 18 is noble gases. That's never going to change.
Noble gas.
Yes. Calcium is a metal. Calcium is an alkaline metal. So you can't, every periodic table, if you're looking at this periodic table, is that true?
Yeah, I did.
Okay, so you can't just base it on color, right? Because isn't this yellow?
Yeah.
Yeah, and this is kind of like a gold, right? They try to make it a gold color so that you think of nobility, right? And so every periodic table is going to have a different way of representing it. You just got to pay attention to the periodic table you're looking at. But don't just memorize colors, because on one color it's going to be blue, on the other color it's going to be gold, you know? So you can't just make those assumptions. You know what I'm saying?
Okay.
Okay.
Yeah.
So pay attention to your periodic table, the one that you're looking at. Okay.
Yeah.
Any other questions?
So, oh, you know, like on metal character BA and CA. Can I put CA first
For
instead
metal,
BA? Yeah, metal.
for metal characteristics,
Yeah, can I put CA first?
nope. CA
No?
would go first, right?
Oh yeah, huh? Okay, got it.
Yeah.
Yeah.
Because the one that's bigger, because the thing about metals, right? So the bigger that they are, the more metallic they become, right? So and this guy is bigger than the calcium.
Yeah, it's bigger.
Yeah.
This one can be a couch.
Sorry. Barium is bigger than the calcium. Okay. Any other questions? Okay, great. So was that a good learning experience?
Yes.
Yep.
Good. So you guys, that'll be my next test question.
Do it.
And focus on the
Okay, let's go. Chapter 12. Okay, so what do you guys remember about ions? What are ions?
Ions could be positive or negative.
Okay.
Well, that would positive would be
What do you mean by that? I mean,
so positive ion.
positive attitude.
A positive ion will have a positive charge, so it'll the atom will lose either one or more electrons, and then if it's an anion, which is a negative charge ion, the atom will gain one or more electron.
Okay. Okay, so what do we call a positive ion?
Cation.
Ion.
What do we call a negative ion?
Non-ion.
Anion.
Okay. So you guys actually do pay attention to me sometimes. I'm starting to feel loved a little bit. See how much more love you guys can give me. So we've already talked about ions, so we don't really need to go into a lot of details, right? We've talked about how they're formed, right? And so how the elements will form ions because they want to be like that noble gas. They want to have that stability, okay? So these are just basically the formation of the monatomic ion, okay? So if we're looking at nitrogen, which we're looking at nitrogen right here, how many electrons does nitrogen needs to gain to be like a noble gas?
3.
3.
3, right? So it's going to gain its 3. So then it's going to gain its 3. What is going to be nitrogen's charge?
The negative.
Negative.
-3, right?
Yeah.
So don't forget that 3. So this is basically showing you that, and it's also showing you the Lewis dot structure for that. You guys remember your Lewis dot structures?
Yes.
Good. We'll see how much it changes when you work with the ions here in a second. Okay, so in the case of hydrogen, so how many electrons does hydrogen needs to gain to be like a noble gas? Gain or lose?
1.
1.
Really? 1?
You say hydrogen, yeah?
I did.
-1.
-1. Okay, so hydrogen has the option of gaining an electron or losing an electron, right? Because it's kind of an odd spot. If it loses 1, it's not going to be like helium. It's going to be like its own special ion, right? So hydrogen is kind of a weird guy, okay? So he has the ability to lose an electron or to gain an electron to be like a noble gas, right? And most cases, hydrogen, if it has a preference, right? In most cases, it's going to want to lose an electron, so it will be a unique noble gas, okay? So its own special noble gas. He's like, I want to be an individual, okay? And we'll talk about that a little more when we start talking about acids. What about oxygen?
To gain 2.
Gain 2?
Yeah.
So did everybody understand why oxygen wants to gain 2?
So it wants to be a noble gas.
Because it wants to be like the noble gases. That's right. And it is only 2 away. If you look on the periodic table,
Being neon.
yeah. Neon is that cool kid.
You guys still going core drive?
Okay, so here's oxygen, 2 away from neon. So it's easier for it to gain those 2 electrons and be like neon than for it to lose 6 electrons and be like helium. So it's always going to go the easiest route. Okay, so what about selenium? Named after Selena.
Would it gain 2 or lose 2?
Gain 2 electrons.
It's going to gain 2 electrons. So we know it's not going to lose 2, so this is where it's located. Losing 2 just makes it like germanium. Germanium is even a hot mess than selenium is. Germanium is a little bit poorish, so hot mess.
Dr. Henry, I have a question. When
Yes.
we say it's going to gain 2, is it going to be written -2?
That's right. So we write it as
-2.
C minus 2,
Okay.
right? Because it's gaining 2 electrons. And we know that electrons are negatively charged,
Yeah.
right?
Yeah.
So,
Okay.
Dr. Henry, are we wanting to gain 2 to become like a noble gas because noble gases have 8 valence electrons?
That is correct. And that's stability. So if you have 8 electrons in that outer shell, that's stability. That's what you want to get to, right? That means that you have all the riches in the world. You're happy. So you're going to try to find ways of getting there, right? So either you're going to steal from somebody, like electrons are just not running around in the streets and stuff like that. You have to take it from somebody, right? So you're going to either take it from somebody, you're going to give it to somebody, or you're going to share it with somebody. So that's what we're building up to, is that bonding, right? So bonding is either going to be the taking or giving, or it's going to be sharing, okay? So those are your ways of getting to that noble gas. It just doesn't happen magically, right? So but we need you to understand that's where you want to get to, right? That's where nitrogen wants to get. That's where oxygen wants to get, right? They want to find a way of being stable. So they're going to find ways of doing it by either meeting up with somebody and hooking up and getting together and staying together, or taking it from somebody, okay?
Dr. Henry,
Yes, sir.
if these elements, they are noble gases, and because you say they are stable, what are the benefits and what ways we can use them to create something or to do something? What is
Well,
that?
in most cases, since they're stable, like for instance, we have neon signs.
Mhm.
The stability allows neon signs to last for a very long time. That's one of the reasons why we use neon signs rather than using oxygen gas signs, because oxygen gas isn't stable. It's flammable. It'll blow up. Where neon signs isn't going to be flammable and blow up. It's happy the way it is. It's stable, so it's not going to really want to react. The only time that your noble gases will react with something is if they get forced to do it, right? So let's say you have, fluorine. I told you guys about fluorine being a bully, right? Fluorine will punk a noble gas, right? You're going to do what I told you to do because fluorine is a bully. Fluorine is so anxious that he's not even scared of the noble gases. He will mess up a noble gas, literally mess up a noble gas. And I'll show you that here in a second, if you bear with me. Okay, you guys good so far?
Yeah.
Nobody wants to jump off a bridge yet, right? Or start drinking at 9 in the morning yet. I'm getting there, but you guys can't.
Who drinks 9 in the morning?
Who's drinking at 9 in the morning? Well, I am not there yet. I'm working on it though. Okay, so far, not too hard. You got the concept of the formation of they call it monoatomic ions. Okay, so you see that word isoelectronic? Did you see that word on that slide?
Yes.
You see it up there?
Isoelectronic.
Do you want me to underline it for you right here?
Yeah. Okay. Yeah.
I'll circle it. Isoelectronic means same number of electrons.
Okay.
So your goal is, right, as oxygen, you want to be isoelectronic as neon. You want to have the same number of electrons as neon does because neon is cool, neon is stable. So you want to have exactly what neon does. Isoelectronic means at the end of the day, you have exactly the same number of electrons, which means that you'll also have the same electron configuration. Okay, so you want to test this out? You want me to prove it to you?
Yeah.
Okay, so let's do it with oxygen. So if we have O2 minus, what is the electron configuration of O2 minus? Come on, you just did this yesterday. You can't forget electron configuration.
Brackets, HE, 2p4, 2s2.
So 2p4.
Yeah.
Mm,
2s.
Oh, I totally skipped 2s. 2s2, 2p4.
Yeah, 2s2, and then yeah.
2s2
and 2p4.
So that would be of oxygen. So what would it be for O2 minus?
The same thing. You just add 2 to the 2p4. It'll be
Okay.
2p6.
So it'd be 2p6. Okay. So this is for oxygen. We'll write the one for oxygen. And that's a HE. I know my E looks funny.
Dr. Henry.
Yes, sir.
Where do you get 2p6? If it is, I know you say that because it has the O2 -2, and it looks like a -2. So where you get 2p6? I understand that comes out the first one, the 2p6, and then it's gonna go to 2p1. What?
No. So we have a 2 minus here, right?
Got it. Mm-hmm.
Okay. So this is oxygen normally. This is what it is. It's HE, 2s2, 2p4, right?
Okay. Oh, that's a 4. Okay.
That's a 4.
It looks like a 1 from here.
That's a 4.
Oh, okay. Yeah.
Stop making fun of my 4. Okay.
Sorry.
So 2p4, right?
Yeah.
So
in the original state, it's gonna have only, for the Lewis dot structure, only have 6 dots. But since you are adding 2 electrons to oxygen, it's then gonna have 8.
that is correct, right? And you want to get 8 around you. Now let's look at neon. What is the electron configuration of neon?
One is 2.
2.
2
No,
is
let's do it with the noble gas core, just like we're doing it.
okay.
You just put NE in brackets.
I'm gonna just put NE in brackets.
isn't
That's
it?
It's already noble gas.
Isn't it HE in brackets?
Yeah,
HE in brackets.
that's correct.
So let's do it with the noble gas before it. Even though what you're saying, Ryan, is correct, it's better to see what you're looking at, right? Because we could have just put this as NE in brackets, right?
Yeah.
So then what is it?
2 is 2.
2s2,
2p6.
2p6.
Okay, now look at these two, right? Can you tell them apart?
Same thing.
They're the same.
They're the same thing. So that's an example of isoelectronic. They're exactly the same number of electrons, but we know that they're different atoms that you're starting out with, right?
Yes.
Okay. So we know that this one is O2 minus and this one is neon. We know that oxygen has how many protons?
8.
8.
8,
And neon has how many protons?
10.
10.
Okay, so they're different, right? The only thing that they have exactly the same number of electrons. So this allows oxygen to be stable, but they still have different characteristics, even though that it's stable with that -2 charge. Do you understand?
Yes.
Okay, so isoelectronic. Okay, you guys get that?
Yeah.
And so this basically shows you that once we form ions with all of these elements that want it to be like neon, they're going to have the same electron configuration as neon. Okay,
Yes.
so I'm going to clear it. Okay, so let's move on. So that's the same thing that happens on the other side, right? Here we have sodium, manganese, and aluminum. So on your periodic table, we have sodium, manganese, and aluminum. So what are these guys, what are they going to do? Are they going to want to gain electrons? What type of ion are they going to form if they have the ability of getting electrons or losing electrons?
Losing.
Lose an electron.
Losing electron. How many is aluminum going to lose?
Going on 3.
3.
Okay, so yeah, it's going to lose 1, 2, 3. So it end up being like neon. How many about magnesium?
2.
2. 1, 2. And then we have sodium.
1.
Okay, piece of cake.
Yes.
Yep.
Okay, so in that case, they're going to have, after they've done that, they're going to have the same electron configuration as neon. So that's what this, what we're showing you here, right? Exact same electron configuration as neon. Okay, so aluminum, this is what it is normally. And then after it's losing its electrons, it has the same electron configuration as neon. That 1s2, 2s, or we could put helium, 2s. Okay, piece of cake?
Yes. No.
Okay, let's see. And you see how we draw the Lewis dot structure here? Oh, man. I'm having trouble with my mouse. There you go. Okay, so this is just basically showing you some of the ions that can be generated. Now, again, these guys are transitional metals. So this is the one that's most common, but there will be some exceptions here. Okay, so and this shows you the common ions that they form. Okay, so write the electron configuration for the calcium ion. This should be a piece of cake. And you guys can use the shortcut way. Even though I don't show it. Who's my volunteer?
I'll do it.
I do.
Okay, Ryan.
So you want the electron configuration for calcium?
The calcium, do the electron configuration for calcium and the calcium ion. What type of ion is it going to form? A
The
cation or an anion?
gonna be a cation.
Okay.
So the electron configuration would be. Do you want me to annotate your screen?
Mm-hmm. Yes, please. So you should also always start off with the element that we're doing, right? Because that kind of helps us out.
Okay.
Reminds us what we're doing. And remember brackets.
Oh, did I mess up on the second one after it?
Yeah.
I don't know if it's gonna.
If you click on the select button and double click on it, you should be able to make adjustments to it.
Select.
And click on the text, that you're trying to fix.
Not letting me. Here. Let me just retype it.
So how many of you guys used Zoom before? And used Annotate? Well, Ryan is working hard, of course. That many?
I've never used it before this class. This is my first time using it.
Really? Was it is it a good experience?
Yeah, it seems pretty easy.
Yeah.
First time too.
Your first time too?
Yeah, it's very helpful in the room.
Dr. Henry.
Yeah.
So I have the one written like in its normal form. I'm just kind of, when you get to the second form where I'm adding the two cations.
Yep.
Is it written the same? It's not, is it written the same way or is it written?
I don't know. That's what we're here to find out.
I think it'd be Ca2 negative, wouldn't it?
Yeah,
Okay. Is it 2 negative? Ca2 negative?
Plus.
I'm sorry, 2 positive because you're going the other way. You're
That's
going
right. So it'd be Ca2 positive, right?
Yeah.
And what does that mean?
That it has
that you're
cations.
There is some isoelectronic.
That you're losing too.
If you click on this select, you can put that 2 plus as a superscript next to your Ca and just move it over.
I don't even see a select button.
Let's see if I can do it. It's a plus. It looks like a plus.
Okay. So then you want me to then write the Lewis dot structure?
No, not the Lewis dot structure, the electron configuration.
Okay.
I'm confused in that part. How do you know it's Ca 2 plus?
Okay, where is calcium located? Let's pull it up.
Oh, in the second group.
Would it be 4s? No, it wouldn't be -2, I don't believe.
Okay, so we're right
you would
here.
just put the AR in brackets.
Just, okay.
Yeah.
So calcium is right here. It's going to be losing 2 electrons, right? So 1, 2 to be like argon.
Oh, okay.
Okay, because it's a lot easier for it to do that than gain a whole bunch, right?
Okay.
So I'm gonna. You're trying to make my life hard, aren't you? I do all of your
If
cleanup
I had a
work here.
select button, I would move it. I just don't see it on my end.
Okay, so that's what it's going to look like, right? Because we got rid of the 2 electrons. You guys see that? So this is what calcium looks like. This is what the calcium ion looks like. It looks just like argon, right? Or if you're writing it the long way, I'll show you it the long way. You guys are so quiet, you're worrying me a little bit.
Oh, the original way. There you go.
Okay, so it would be considered, since it's exactly argon, it would be isoelectronic to argon, right? Which in this case has the same number of electrons as that calcium ion. Piece of cake?
Yes.
Okay.
Yes.
Okay, so now we get to talk about ionic compounds. Now that you guys understand a little bit about ions, so again, tell me what an ion is.
Charge.
It's a negative or positive charge on
Okay.
an atom.
Okay, and what makes it negative or positive?
The cation or the anion.
But what makes it a cation? What makes it
The
an
electrons.
anion? What about electrons?
If it gains electrons.
So if it gains electrons, it's what, a cation or an anion?
Anion.
Anion.
And if it loses electrons,
Cation.
Cation.
you guys understand what I'm asking for in terms of those definitions? Yes, no, maybe?
Loses electron as an anion and gains electron as a cation.
Are you sure?
No.
Doesn't it have something to do with the charges? Like the
Yeah,
plus
yeah,
and
but-
minus
Does it
charges
have the-
between like with them?
Okay, so you guys we're going in circles here, right? So let's start talking about, let's just write it down. I asked you what an ion is, and you told me positive and negatively charged atoms, right?
Mhm.
Great. So what makes them positively and negative charged? And then you said, oh, cation and anion. So a cation is that a positively charged atom or is that a negatively charged atom?
Positive.
Positively
It is a positively charged. So are they gaining electrons if it's positively charged, or are they losing?
Oh, you're going to
electrons?
lose an electron.
losing electrons.
Okay, so cations loses electrons to get their positive charge, right?
Yes.
Yes. Okay, anions gain electrons to get their
Negative.
negative charge, right? Okay, piece of cake?
Yes.
Yes.
Okay, good. So now we get to talk about the ionic bond. Okay, so remember when I talked to you about positive and negative, and you always go for that boy that's always the opposite of you. So if you're a negative person, you're gonna go for that positive person. And if you're a positive person, you're gonna go for that negative person. Opposites attract. Yeah?
Yes.
Okay. So if not, I'll give you a refresher, right? So I told you, how many of you guys dated in high school or in high school and are dating?
Not me.
Or in middle school? Some of you guys start early, I know. Okay. So all of you, right, have dated at one point?
Yes.
Stephanie,
Yes.
I'm calling
Yep.
you out. Stephanie and Jocelyn, you guys are doing your nails. I'm talking to you. Don't pretend I'm not talking to you. So have you dated?
No.
Stephanie?
No. No.
Uh-huh, that's what she says. Uh-huh.
No.
She knows she has a secret boyfriend. You want me to call him out?
What?
Okay. Jocelyn, you have a secret boyfriend too? That bad boy that you had that big crush on? You're not answering, Jocelyn, either?
Oh no, I don't have no boyfriend.
Uh-huh. That's the mom and dad must be around.
No.
They already told them. They already told them, nope, you can't see that boy. He comes from that bad family, you know? Mm-hmm. Okay, so, and they know that, you know, when mom and dad ain't listening, well, I love him, right? Because he's the bad one, right? So those opposites are going to attract. That's what it ends up being. So in this case, your positives, you guys already know how to establish your positive. Your metals here are going to be positive. Oops, I'm clicking on the wrong screen. So my metals, all my metals are going to be positive. They're going to have a positive charge associated with them. So, and my non-metals, these guys, are all going to end up being negative. So when I get a positive and a negative together, they're going to attract to each other. And they also are going to balance out each other, right? Okay, so we want to set them up so they balance out. So the fact that you have two ionic compounds, like we have, let's say, sodium, Na, Cl. This is an example of an ionic compound because Cl is going to take the electron from the sodium. So it becomes minus, and the sodium is going to give it up because sodium loves chlorine. So it's going to become a plus. And so when you have a positive and a negative, they're going to come together to form our ionic compound. So what is NaCl?
Sodium chloride.
Sodium chloride. What do we know it as?
Salt.
Salt, right? Now, remember I told you that sodium by itself is very reactive. And chlorine by itself, chlorine gas by itself is really reactive, right? So why can we eat salt? You guys eat salt? You put it on your food?
No.
You don't put salt on your food.
No.
You lie.
I eat salty things.
Oh, do you eat potato chips?
Yeah, I
Popcorn?
love potato chips.
Uh-huh. Why do you love potato chips? Do you eat
Because they're
saltless-free
salty.
potato
I'm
chips
a
because they're
salty
salty? I thought
person.
you said you don't eat salt on your food. So you just lied to me, David.
No, I like it. Ryan said he doesn't.
Oh, Ryan?
I'm
Ryan,
I'm
do
the
you
one
eat?
who's gonna have high blood pressure.
Okay, Ryan, do you eat salt? You don't eat salt? You don't eat potato chips?
I eat potato chips, but I don't add extra salt to my food.
Oh, but you eat potato chips because they're salty, right?
Correct.
Otherwise, it's fried potatoes, and you know it's okay, but it's still not the same. How many of you guys eat mashed potatoes? You love mashed potatoes? You love mashed potatoes by themselves where nobody added any seasoning? Or do you love mashed potatoes with that gravy, that salt, that pepper, that butter? Right? It's because of the salt. You know, we all love salt. We can't deny it, you know, it's in our system. Okay? So now the thing is, salt is stable. The reason why it's stable is because we have those positive and negative charges that happen, and we're also having them coming together. So it adds to its stability. And so we're able to get something that's totally poisonous that will kind of blow up in us to be something that we can have, you know, in a diet and taste great, right? Because they're interacting with each other. They're reacting with each other. Okay, you guys get that?
Yes.
Okay, so that's going to be kind of important. So remember that concept. We're trying to get stable. So these guys, not only did they get stable by giving up, like sodium gave up an electron, right, to be like a noble gas. And chlorine took that electron to be like a noble gas. Okay? So, and then because of that, they become charged. And as soon as they become charged, they get together. They're perfect for each other. Okay? So, let's say we have manganese and chloride. Okay? So, chloride is going to do what? What is it going to want to do?
Gain.
It's going to want to gain an electron. How many electrons?
One.
One. So it's going to want to be negative. And then magnesium is going to want to do what?
Lose.
Lose. How many?
2.
2. So it wants to get 2 plus. So magnesium is going to want to have how many chlorines to balance it out then?
2.
Yeah. So it's going to hook up with twins, right?
Yeah.
Because magnesium is one hell of a woman. She can handle 2 men. So she's always going to need 2 men to balance her out. Okay? So let's look at aluminum. And let's stay with chlorine. Keep it simple. I'm going to erase this up here so we don't get a little confused. So we have aluminum. So what is aluminum going to want to do?
Gain 3.
Lose 3?
No.
Lose 3.
It's going to want to lose 3. So it's going to be a 3 plus.
Plus.
And so she's going to give an electron to 3, to triplets, right? So she's going to be, together, It's going to be AlCl3, because in this case, aluminum is even more of a woman than magnesium, and she needs 3 men to handle her. No, 1 isn't enough. She needs 3. So she needs to be balanced out completely. Okay, so she can be satisfied. You guys get that? You see that, Anna? You see it, Anna? Are you there, Anna?
Yeah.
Okay. You guys see it? Deandra?
Yes.
Yeah. Piece of cake?
No, no.
No? You don't see it?
How comes AlCl3?
Because
you have to go 4 to go to the 17.
look where Al is located at.
It's 13.
It's 13, right? So you have an option of gaining 1, 2, 3, 4, 5 electrons, or losing 1, 2, 3. Which one are you going to do? Sorry.
I lose 3.
1, 2, 3.
But how about, you know, the Cl, if I lost 3?
No, we're not talking about Cl. We're talking about Al. Look at Al.
Yeah, I know. Yeah, 3. How about
Okay.
Cl?
Where Cl's right here. If you want to be a noble gas, are you going to want to lose 1, 2, 3, 4, 5, 6, 7 electrons, or you just want to gain 1? Which one do you think is going to be easier? Gaining 1 or losing 3? 1, right? So Cl is going to take that 1 from aluminum. This one takes it, but there's still 2 electrons left. So this one takes it, and then the other takes it. Okay, so you have 3 of them to 1 Al. Right? Because here we had 3 electrons that it was giving away. 3. So E, 3E. Okay, 3 electrons that were given away. The first one takes it. The second one is going to take it. And the third one is going to take 1. So each one of those get an electron from aluminum. Because aluminum is more of a woman. She has more to give than each 1 Cl does, that 1 Cl can take. So each one can only have 1 electron. You understand? To be like a noble gas. You don't want too many. You just want to be like a noble gas.
Okay.
Okay? So that's the reason why it's 3. 3 plus, minus, minus, minus. Add up these 3 minuses. What's going to be that?
0.
Altogether, it's going to be 0. So altogether, your overall charge on that compound is going to be 0. And that's the goal, because 0 means stability. Okay?
Okay.
It's another form of stability. Okay? So that's the same thing when we did the sodium, right? This one was +1. This one is minus. Right? You put them together, 0.
Yeah.
Same thing down here.
So
Magnesium chloride, 0. So your goal is to get a total for a compound. You want to be at 0. That's the best place to be.
Okay.
It's okay for you to be charged if you have to be, but you don't want to be, right? Because you want to be normal, right? 0 is normal. You know? And so you kind of think about it, right? If you meet a person who's always positive all the time, wouldn't that get on your nerve? Right? They're never sad. You go to them, you're like, my brother got killed. And they say, oh, yes, it's great. That's a happy thing, right? You can think about all of the things. Now he's up in heaven and all this stuff. And you're like, God damn it, my brother just got killed. I want a little sympathy. I want you to be sad with me for a little bit, right? You don't want all of that cheerfulness all the time. It'd be kind of crazy, wouldn't it? And so you want somebody that's going to balance them out, okay?
Okay.
Any other questions?
Nope.
Nope. Piece of cake? Yeah, no, maybe.
Maybe.
Until you make it harder.
Until I make it harder, of course. I'm going to make it harder. Okay. So let's start off with, let's say we're doing, let's say we're going to work with nitrogen. Is going to be our are non-metal. And then we'll do metals, let's see, we'll do lithium. We'll do calcium. And we will do aluminum again. Okay. So let's start with lithium. So what's going to happen in the case of lithium and nitrogen getting together? They meet up in a party and they're like, hey, I kind of like you. What's going to happen?
They attract.
They're just going to attract?
Well, lithium has a positive associated, and
Okay.
nitrogen needs, I think it says it needs 3 more.
Okay.
So we'll
So
need 3
It's going to be a
lithium.
plus. And then you said nitrogen is going to be 3
It needs-
minus.
Yes,
right?
it needs 3 more.
Okay, so I'm going to need to get how many lithiums then?
3 to balance
Okay. So
nitrogen.
now nitrogen is too much of a man for 1 lithium. It needs 3 to balance it out. So 1, 2, 3. So we get Li 3 N. Okay, you guys see that?
Yes.
Okay, what about calcium?
It'll need a gain 2
Have to lose 2.
or lose 2.
Okay, calcium needs to lose 2.
Yeah.
And nitrogen
Needs to gain 3.
okay, so how is this going to work, right? For it to be balanced out. Do you guys remember doing something like common denominators?
Kind of.
Kind of?
Yes.
So you guys don't remember, let's say I have 1/3 plus 1/2. I said that backwards, I know. So how would I do this?
The common denominator would be 6, wouldn't it?
Common denominator would be 6. So how did you figure that out?
You'd multiply the bottom 2,
Okay.
and then you would whatever you multiply the bottom by. So let's say to get 6 for the 1/2, you gotta multiply by 3. So you'd multiply your top 2.
Okay. So you're saying if I was going to do this, I need to multiply both the top and the bottom by 3. Is that what you're saying?
Correct. And for the other one, you would multiply by 2.
Okay. And then I can do it. So you're going to do something like this, similar to this in chemistry. The best way of doing it is take that number and use that as your subscript. Instead of using positive or negative, we're going to use absolute values. So then you're going to get calcium 3, nitrogen 2. And so if we want to check to see if it balances out, so each calcium is 2 plus, is that correct?
Yes.
Each nitrogen is 3 minus. Okay, so let's do all of that adding together. So that's, oops, sorry. So that's -6. And 2 plus 2 plus 2 is what?
Positive 6.
Positive 6. So it works out. So
Yeah.
that would be my answer.
Balance.
Okay.
So you kind of, so when you, can you kind of just go over that one more time when you do the, is it cross denominator? Is that how you did it?
Yep. So
So
I took the charge, right? And since they don't balance out normally, I just cross multiply it. So I make this my subscript. So then That'll be 3, so that means I need 3 of those. And then I put the 2 over here because I need 2 of those. And so it just works out. Sort of what you're doing here with the other place, right?
Okay.
So altogether, you think about it, it's 6. So because each of these are, it's just by multiplying it by that number right there that you're going to get. Same thing, right? 1, 2, 3 of those, 3 calciums, 2 nitrogens.
Dr. Henry, when you cross multiply, minus 3 becomes plus 3.
So no, you're minus 3. So you're not multiplying it by the minus part. You're taking like the absolute of it.
Okay.
So you're just saying using 3. So you're using just the number. You're not using the charge.
Okay.
So for your subscripts, you can never have a minus, ever, right? So you're just taking the number that it is. It's 3 there, it's 2 there. So you just multiply by that, and then you'll get the number that you're going to need. Do you understand?
Yeah, thank you.
Okay, so let's see, what about AL?
Aluminum?
Aluminum has a +3.
It's going to have a +3. Nitrogen is going to have
a -3.
So then how many am I going to need then?
3 and 3.
I'm going to need 3 and 3? Doesn't +3 and -3 balance each other out?
Yeah.
Yeah.
So I'm just going to have AL
And
N. Piece of cake?
I do.
Okay. So how are you feeling so far?
Okay.
Okay.
Mm-hmm.
Okay, so let's see if we could go on a little bit. We'll come back to this, don't worry.
So Dr. Henry, what do you call ALN?
So that's a compound, that's the ionic compound. So together they form an ionic compound. Individually, they're just ions.
All right.
Right? And they want to come together to form an ionic compound. So your job is to form that ionic compound, right? You're going to figure out how are they going to balance each other out, okay? So if you read the instructions here, or not the instructions, read the lecture notes. So basically, we've talked about 2 ions coming together. They form what we call an ionic bond. Now this bond is a pretty strong bond, long as there's nothing that's going to get in its way. And we'll talk about that here in a minute, right? So, but when there's stuff that could kind of get in its way, because those things are positive and negatively charged, if you find something that can come between it, right? Like water. What happens when we put salt in water?
Dissolves.
It dissolves, and it separates them into their 2 ions because water is a home wrecker, right? So salt was all happy, nice together, and as soon as water comes into play, it separates it. And I'll explain that to you a little bit later too. Okay, so almost all ionic compounds are solids at room temperature and normal pressure. But normal conditions, they're almost always a solid. And these solids, they often will have a crystalline structure. They're pretty organized in how they're arranged. And so they're going to form a crystalline solid in most cases. And then we'll often call this a lattice. So it'll be a crystalline lattice. So they have a very defined structure. It's very organized, okay? So now, again, that's long as there's nothing else around. As soon as water comes into play, or sometimes alcohol comes into play, it can dissociate those things, okay? It'll break up that relationship, so they won't interact with each other. Okay, so we've already talked about, you always want to balance out those charges. So an ionic compound has no charge associated with it, right? They've come together to balance each other out. Okay, so they should have a total altogether a charge of 0. So you guys remember, we don't write sodium chloride, and I'll tell you guys this, and I swear to God, there'll be at least 25 people in the class that does it. We never write it, so we write them as their ions like this, But when they come together, because they're balanced, we don't write the charges. It's understood that they have those charged and they're just together. You guys see that?
Yes.
Yep.
Okay. So that's going to be important. So at the end of the day, they come together so that they can be neutral, electrically neutral. Okay? So they balance each other out.
Dr. Henry, will this be on the test?
This will not be on the test. We can't stop. We're going to keep going. I'm going to keep throwing stuff at you. You got to keep retaining it and everything like that. This won't be on the test. This will be on your next test, but you need to know it.
Okay.
Okay? So that's the thing about summer. We don't have time to stop and then to digest. There's no digestion time. You're digesting as we go, right? It's like eating on the run. Okay, so the bonds, like I told you, they're going to be strong. It's a strong bond. It's not a weak bond, but it can be dissociated by water. Most of them can be. And they still can serve as a very good conductor if there's water present, right? If they're not in water, they're shitty conductors, right? And that's the funny thing, because you have a metal and a non-metal. You'd assume that, oh, I have a metal and a non-metal is going to be kind of balance each other out in terms of their conductivity. Nope, they're horrible conductors when it's just the solid. But when they're in water, they're really good at conducting because you have those charges, okay? You guys get that?
Yeah.
Okay, so this is just basically showing you the reaction between sodium and chlorine. So they're very quick to react. And so that's how you get those electrons exchanged, because one of them is really, really hungry for it. And the other one is like, hey, you can have it, go ahead, you know? And this is just showing you the exchange of those electrons. So chlorine is getting the electron from sodium. So then sodium becomes plus, and then the chlorine becomes minus. This is a picture of what it would look like. The crystalline structure is going to look like. So you have alternating positive and negatives. This is a salt crystal. Look how beautiful that is. This is just showing you the lattice, right? So again, the bigger one, the green one, that's your sodium. That's your chlorine. The black one is your sodium. And so you're having alternating between your sodium, and it's just they're interacting by charges. And so since sodium is all around it, it's going to be a positive charge. So it's going to be attracting the chlorine, but it's going to attract it in an orderly fashion. So you're going to have a chlorine here, you're going to have a chlorine there, and you're going to have a chlorine there. This sodium is going to be surrounded by chlorines on all four sides. And so on and so forth, right? So the chlorines are going to be surrounded by the sodiums, okay, the sodium ions. You guys see that and understand that? So this guy here, you guys didn't say anything, so I assume that you understand it. So I'm just going to move on and just keep on talking and pretend like you guys, because you would have told me at this point, because you guys aren't shy. So this is like a big plus, right? A big, huge plus. So it's going to attract, this big, huge plus is going to have positives. A negative, a negative, and a negative, and a negative, right? So it's going to be surrounded by 4 points of negative, 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 okay? Negative. So negative in a three-dimensional structure, it's going to be surrounded by that. So then this negative is going to be surrounded by positives, right? Because that's what it's going to charge, because the overall thing is, and so they're going to be alternating positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, because they're still going to be interacting with other things, okay? So in reality, an ionic compound is really just a whole bunch of positive and negatives interacting with each other through it, not just one together. Although that's how we want to define it, because it's easier for us to define it, and it kind of works out chemically that way, numerically it works out that way, right? Because they end up balancing each other out, right? But in reality, it's a whole bunch of them interacting together to form that complex. Do you guys understand that?
Dr. Henry, I have a question.
Yeah.
So when we look at the ball and stick model number 1 and how we have the Na and the Cl, so if one of those, say the black atoms was green, would it mess up the overall structure of that element?
Yes, because what if you have two greens that interact with each other? What happens? What is the charge on green?
Would they repel?
It's going to repel. So it's going to cause a kink because it's going to be pushing everything away from it.
Okay.
Okay?
Thank you.
So, and typically it'll rearrange itself because it's still dynamic to sit there and get that a positive charge there instead of a negative charge. Okay? So, but that's a good question. Good question. Okay, so this is just showing you that liquid sodium, so sodium in water is going to be able to conduct electricity. In this case, they heated up an ionic compound high enough so that it actually melts and it'll actually conduct electricity. Right? So you don't necessarily need water, but if it's in water, it does a great job of conducting electricity, or you have to heat it up to really, really high temperatures to get it to melt, and it will actually conduct electricity. Okay? In its liquid form. Okay, are you good on ionic so far?
Yes.
Okay. It's good. I'm glad I have a class of 1. It's so easy. That should be easy grading for me. I'm going to grade 1 person then. That's it. Okay, covalent bonds. What covalent is basically you're sharing electrons. So it's basically a bond between 2 or more atoms where you're sharing electrons. So nobody owns it completely. It's not like, you know, like with ionic, one gives away an electron, the other one takes it, right? So sodium gave it away, chlorine took it. With covalent, you're sharing. Okay, so the most commonly known one, even though they show hydrogen here, the one that we always talk about is H2O. Okay, H2O. What is H2O?
Water.
Water.
Okay, so I'm going to draw the Lewis dot structure. Hydrogen has how many electrons? How many valence electrons does hydrogen have? One. So if I drew its Lewis dot structure, how many electrons would it have?
1.
Oxygen has how many valence electrons?
6.
6.
Okay, so I have 1, 2, 3, 4, 5, 6. Okay, and we have 2 hydrogens, so I'm going to put another hydrogen here, and it has how many valence electrons?
1.
Okay, so remember I told you that everybody wants to be like the noble gases, right? How many valence electrons did the noble gases have?
8.
8.
8. It wants to form what we call the octet, okay? So hydrogen is kind of special. For it to reach its octet, it needs to have how many valence electrons to be like helium?
2.
More?
2.
2, that's right. So hydrogen can only form 1 bond, right? So what happens is, when we draw this line, that means it's sharing those electrons. So those electrons are being shared between hydrogen and oxygen. Okay?
Dr. Henry, whenever you connect those lines, would there ever be a situation where you connect the lines to the double dots on the bottom? Or do you always want to do 1 dot per 1 dot?
You always, well, sometimes you're going to have what we call a double bond, right? And we'll talk about that here in a second, I promise you. But right now, we're going to talk about the single bond, and then we'll get to the double bond. You're ahead of the game. But yes, there will be times like that. Now, the way you determine whether or not you're going to use 1 bond or 2 bonds or 3 bonds is because you want to try to obey the octet rule, right? As much as you can, you want to obey the octet rule. There will be exceptions, right? Because we're in chemistry, there are always going to be exceptions. But you want to try to obey the octet rule, okay? So if we look at it now, so these guys are sharing electrons, meaning that these electrons are being shared between the 2. So if we count the number of electrons around the hydrogen now, number of electrons around the hydrogen, so the line represents 2 electrons, okay? Because it's being 1 oxygen is donating one to be shared, and hydrogen is also donating one to be shared. So how many electrons does hydrogen have around it altogether?
2.
2. Okay. This hydrogen, how many does it have around it altogether?
2.
2. Okay. Now, this oxygen, how many does it have around it altogether?
6.
Count them. Because remember, this represents how many electrons? The line represents how many electrons?
2.
2. So that's 2.
8.
8.
8. Okay. So that means it obeys the octet rule. It's like a noble gas by sharing those electrons. It's stable. You guys see that?
Yes.
Okay. So your goal is to try to get to your octet. Okay. You want to be like the noble gases. So either you're going to get like the noble gases, like sodium chloride did by giving up electrons or taking electrons, or you're going to share electrons. Okay. And there's 2 forms of sharing. How many of you guys have siblings? I want to hear, I need to hear verbal commands.
I do.
I do.
I have siblings.
Because remember, I have 21 people I have to look at. I can't see you guys all on one screen. So all you guys have siblings? Anybody who's the only child? Nobody's an only child? Good. So this makes it easy. Okay, so I'm going to explain something to you, and I want you to think about it, right? So who's the oldest of your siblings? Are you guys, any of you guys the oldest?
I am.
You are? You are. Okay. So my parents, because we were poor, we often would get one group, we would get a big present that we would have to share. That would be like a Nintendo or something like that. And then we would get individual presents, right? And so, and often that individual present would be something small or something like that, that is kind of tailored towards us, but it would be one individual present and one big present. And then we would get socks and underwear. That was always Christmas. You're always guaranteed socks and underwear for Christmas. And you get your one toy, your one personal toy, and then your one big toy, right? So during Christmas, since I was the oldest, and both my parents worked a lot. So they were always working. Both of them had 2 jobs when they were in town. My dad was in the military, so sometimes he'd be on the boat. But if he was in town, they both had 2 jobs because they wanted to try to do better than their parents did, right? So, so when my parents were away, I would get the Nintendo and I'd be playing the games and stuff like that. My sisters, can I play? I'm like, no, go away, leave it alone. And I play and I play and I play and I play, right? Now, it's a shared gift. That means that my parents felt that we should share it evenly. Well, but I'm a kid and I'm the oldest brother. I'm bigger at that point, right? So then I'm like, it's mine, right? And then as soon as my mom gets home, I give it to my sister. You see how it works?
Yeah.
Okay, now, are we sharing?
You aren't sharing.
Looks like you're.
What do you mean? They get to play with it, right? Don't they get to play with it? It's not like I just took it up and packed it up all the time, right? But I was smart about how I did it, right? So 99.9% of the time, I had it. And then that 0.1% of the time, my sisters had it. So it was perfect. It was perfect sharing because I was stronger than my sisters, right? I took it most of the time. And then occasionally when my parents came home, they got to play with it, okay? So that is a form of sharing, but it's uneven sharing, right?
Yeah.
It's not fair sharing. We didn't say anything about being fair, right? Life ain't fair, is it, right? So it's uneven sharing, okay? So oxygen is so close to being a noble gas, and it's stronger than hydrogen. It's bigger than hydrogen, it's stronger. It has so much more desire than oxygen does, because oxygen can lose or it can gain an electron to be like a noble gas. Hydrogen could either lose or gain to be like a noble gas. Oxygen only can gain. So it's got a bigger drive for it than hydrogen does. So it's going to be stronger. This is called your electron affinity, right? It's the affinity is the affinity to take electrons. Oh, that's mine, right? So oxygen is pretty strong, right? There's only one person that's stronger than oxygen, and that's fluorine. Fluorine is stronger than oxygen, but oxygen is pretty damn strong. So since that's the case, hydrogen is like, hey, dude, we can share, right? But oxygen is like, yeah, we can share. He just takes it a lot more of the time. So he's kind of like that older sibling that's going to be kind of bullyish, right? Like I did with my sister. 90% of the time it's mine. You can only get it at 1% between my two sisters, right? So, or 10%. So that's what goes on here. It's uneven sharing. So we call that polar covalent bonds. So if it's uneven, it's a polar covalent bonds. But if it's even, it's called nonpolar covalent bond. Okay? Polar basically meaning that since oxygen is stronger, it has a stronger pull for the electricity, so that it pulls the electron closer to itself. So it's going to be what we call partially.
Dr. Henry, you say polar covalent bond is the positive or negative?
No, it's neither. It's sharing, right? So it's not truly negative, and then, but it's not truly positive. I'll show you that here in a second. So this guy is going to be partially negative. Oxygen is going to be partially negative, and then hydrogen is going to be partially positive, right? So all we're saying is that the electrons is going to spend more time around oxygen than it's going to spend around hydrogen. Okay?
Okay.
Can you say that one more time, Dr. Henry? You said the difference between polar and nonpolar?
Yes, please.
The difference between polar and nonpolar, okay? Polar is uneven sharing.
Okay.
So think about siblings.
Okay. And then nonpolar is even sharing?
That's right.
Okay, thank you.
Thank you. There you go.
Okay, and so even sharing. Okay, you guys there? You with me?
Yeah.
Okay, good. Okay, so the bonds with covalent bonds, right? They're going to be harder to break, right? These bonds are permanent. It's really hard to break without a lot of energy. Okay, so it takes energy to sit there and break these bonds. So they're connected, so they're sharing. They're not going to be like, you know how we have those two charges that are interacting. They're not like the ionic, where you can just put water in between and separate it. These are covalently linked to each other. You're going to have to break bonds. They're going to have to be broken to sit there and get that chemical chain. Where adding water to a ionic bond, it just kind of causes it to separate. That's not the case, okay? So these bonds are even stronger than our ionic bonds. They take a lot of energy to break, okay? Okay, so remember when we talked about a molecule? So a compound can be a molecule, right? So we're going to add a little more definition to that. So we could have a molecular compound, right? So we can have an ionic compound, or we could have a molecular compound. A molecular compound is one that forms covalent bonds, right? Ionic compound forms ionic bonds, okay? So molecular bonds, they're molecules rather than the ions, okay? Okay, so here is an example. Here we have pure water. Here we have table sugar in water. Here we have table salt in water. Okay, table sugar is a molecular compound. So they're sharing all of the bonds, right? So I'm not going to draw it out because I'd be drawing for days, but it's basically 2 glucose rings. And well, let me just pull it up so you guys can see it. Okay, do you guys see it on the screen?
Yes.
Yes.
Yeah.
Okay, so this is a nice one that shows you all of the where all the carbons and stuff are located and stuff. So these represents the bonds between that oxygen, and here this will be a carbon here. So bond between oxygen and carbon, they're shared. They're not easily broken. Because of that, right? Because they're not charged, you don't have anything charged, they're not going to conduct electricity. Where in this case, we have sodium. As soon as we put sodium in water, water acts like a homewrecker. Water will dissociate the sodium chloride because remember I told you water is polar. So we have our H, O, H. Now oxygen, they're sharing the electrons, right? But the electron is going to be spending more time with oxygen than it is going to be spending with hydrogen. So it's going to be what we call partially, and this is what this delta, this symbol is called delta. Delta minus means partially negative. Delta plus means partially positive. So you know, like with sodium, when it forms an ion, it's a plus. Okay, so this is a whole plus. It's just plus, right? This one is partially plus, meaning that it's not complete, it's not a full number, so it's kind of like a fraction, right? So it's like a third so depending on who it's paired with, its partial plus can be like a half or a third or less. So it's not like a whole number, right? Where this is a whole number, that's 1 plus. So it's a full ion. So here they're sharing, so we're just saying that the electron is spending more time. The electron is more time on the oxygen, around the oxygen, than it's spending with the hydrogen. So the hydrogen gets the electron every once in a while. So we'll say like 80% of the time it's on the oxygen, 20% of the time it's on there. But that electron is being shared between them, right? Hydrogen gets it, but he doesn't get it all the time. Kind of like, you know, kids that are between divorced parents, right? Okay, you guys get that?
Yeah.
Okay, so now since this is partially positive, and we know Cl is a complete negative, what do you think is going to happen when we put water into salt?
It'll have a reaction.
Well, it does, right? It separates the ionic compound. So we go from a salt, right? That's solid. You guys remember what salt looks like. So what happens when you put salt in water?
Dissolve.
What happens when you put salt in water?
Dissolves and separate.
Doesn't it dissolve when you mix it?
It dissolves. It dissolves when I mix it, right? Because we're breaking up that ionic compound, right? So initially, this is what we have. We have Cl, Na together. So that's our salt when it's all together, right? And then as soon as we put water in here, Cl,
break.
Cl will interact with the hydrogen and the Na. The Na plus we react with or interact with the sodium, because this one has a partial negative charge and this one has a partial positive charge. So these guys are going to interact. And then I'm going to show this interaction as a, let's see, where is it? So this is my interaction. I'm going to show the interaction like this because it's not a bond, it's just an interaction. So this would be called a hydrogen bond, right? It's not a strong bond, But have you guys done a fist bump with somebody? Fist bump?
Yeah.
Yes.
Okay. So are you guys touching in the case of a fist bump?
Yes.
Yeah.
Is that
Yeah.
interacting?
Yeah.
Yes.
Okay. So hydrogen bond is kind of like that fist bump, right? So they're interacting with each other, but it's not a strong interaction because, you know, anything can get through them and break them apart, right? It's not that hard. Where the covalent bond is kind of like an arm, right? An arm that's connected. So you have to cut it off, right? You got to get a knife, sharp knife to cut it off. And then the ionic bond is kind of like a handshake. A handshake, if both people keep their hands intact, it's really hard to break a handshake. When you were kids, you guys used to play red over, send such and such over.
Yes.
Yeah.
No.
You guys never did that? Your generation has missed out on such good things.
Wasn't it like when you would break someone's like they were holding hands and you tried breaking through?
Yes. So ionic bonds is kind of like that. The only thing is like, so if we put oil on people's hands, would it be easier to break than it would be if we didn't have oil?
Correct. It would be easier.
Yeah.
Yes. Okay. So water kind of acts like that. Okay. So water is going to have these interactions between it to sit there and make it easier and separate those two, right? So water is kind of like I said, is a home wrecker, right? You guys know what a home wrecker is.
Yeah.
You know, you have a married couple, and then there's the neighbor next door who comes over and flirts with the husband.
Yep.
You've heard of that, right? Home wreckers. I know you've seen it on TV or something like that. Desperate Housewives, or I don't know what the show is today. I haven't watched enough TV, but there's one like that. Okay, so or you guys watch that? Well, what is that show on MTV? The one about the island, My Ex Island, or whatever that is, Paradise Island, some island where they bring on each other's exes.
No, not really.
Oh,
Okay.
I've seen it.
You guys are hopeless. I can't even talk to you about TV shows
I
anymore.
watched PSP.
Okay. So in this case, right? So water is kind of like, you know, it goes up, and water is playing both parties. So water goes up to chlorine and says, "Hey, baby, you don't need sodium. You got me," right? And then soon as chlorine turns its back, it goes up to sodium. "Hey, baby, you don't need chlorine. You got me." So it's playing both of them, right? So it's separating them. Since it's polar, you know, polar, it has both, it's going both ways, right? So water swings both ways. It interacts both with that positive and that negative, okay? So, and it separates the two. So then they separate, so the oxygen will interact with the sodium, and the hydrogen will interact with the chlorine, keeping them separated. And so that's why water dissolves. By it dissolving, you have these charges readily available. They're easily available. And electricity is just the movement of electrons. So if I put an electron in, it's going to get this guy. It's going to provide an electron for the sodium. And then the sodium is going to say, "Oh, wait. I'm negative again, so I need to become positive." So it's going to try to find a chlorine to pass it on to, and so on and so forth. So then you can propagate an electron through that solution so much easier than when they were connected together where they were neutral. It's a lot harder to do it here. Okay, so ionic compounds can conduct electricity when in water, where when they're solid, they won't be able to conduct electricity. Okay, covalent compounds don't conduct electricity because they don't have those true positive or negative charges. They only have what we can get, at best, we can get partial positive and partial negative. So water doesn't conduct electricity. Sugar won't conduct electricity, but your salt solution will conduct electricity. Okay, you guys see that?
Yes.
Okay, you guys got to wake up. What's wrong today? You guys are sleeping. I see Selena is on her bed. She's already in bed. She's struggling. She's laying out, you know?
Oh my gosh.
I know, it must have been a long night last night. Too much chemistry?
Dr. Henry?
Yes.
So for covalent compounds, they cannot conduct electricity due to how they're not partially like equal or something like that?
No, they don't have complete charges, right?
Oh, okay.
So they lack complete charges. They only have partial, like at best, you can only have partial charges. So if you have partial charges, you're polar, right? Polar molecules have partial charges. Non-polar molecules don't have partial charges. And we're going to talk about that for right now. We're going to expand that definition about polar and nonpolar about when we talk about the whole thing together, because it gets a little more complicated.
Okay, thank you.
Okay. Okay, so really what's happening is that hydrogen's orbital and oxygen's orbital are overlapping. So the electron is able to go through both of those. And since oxygen has a stronger pull, it's going to keep that electron more in its orbital than hydrogen is, right? Although it's still going to go over where hydrogen is, so it's going to circulate the nucleus of oxygen. Okay, so let me show you what that looks like. You see that here? All right. So this is just showing you hydrogen and hydrogen interacting with each other. So this will be even sharing because they're like twins that are exactly alike, exact same strength and everything like that. So you're going to have even sharing in this case. So is that going to be polar or nonpolar?
Non-polar?
Non-polar.
Polar.
That's correct. Okay, so if you look here, so this is hydrogen and hydrogen separated. So when they come together, they're going to be circulating, the electron is going to be circulating both of these. So it's going to be working around it. So you have this, you see this electron density? This basically just shows you where the electron is going all over. So here, they're sharing that electron density, okay? So this is what it looks like. Okay, so you guys, this is basically showing you the Lewis dot structure. So we have the Lewis dot structure of fluorine, Lewis dot structure of fluorine, and then when they're sharing the electrons, because they reach their octet, count how many electrons are around this fluorine.
8.
And then how many are around this fluorine?
8.
Okay, so it's allowed to reach its octet, and so it's able to form a bond. So when you have two compounds or two elements coming together, they're going to try to form a bond with each other so that they're sharing electrons. So if you have two non-metals come together, they're going to want to share electrons. Okay, so the way I like thinking about this is the thief model. That's what I'm going to call it, the thief model. Let's see. Okay, so I like to look at the periodic table like two sides of towns, or the metals and non-metals as two sides of towns or two different towns, right? So are you going to steal from somebody who lives on your block right next door to you?
No.
Let's say they have this really cool ass bike, right? Your neighbor. He has this really, really cool ass bike. It is the bombest bike you've ever seen, right? So are you going to take his bike and drive it around the neighborhood?
No.
No,
Why not?
because the neighbors probably will know what that bike looks like.
Yeah, you take his bike, he's gonna say, man, you stole my bike. He's gonna call the police on you, you're gonna go to jail, right? Real simple, okay? Now, if somebody lives in a town across from you, right? Are you gonna be more likely to take his bike or your neighbor's bike?
The one across town.
Cross town.
So you're gonna take the one across town and you're only gonna drive it in your neighborhood, right? Because in that case, he's never gonna know who took his bike because he never comes into that neighborhood, okay? So metals, okay, let me expand a little bit more. So your neighbor, right? What you're gonna do with your neighbor, if he has a really bomb-ass bike, you're gonna be like, hey man, let me ride your bike. Can't we share this bike, right? So you're gonna be more apt to share with them than you are to not share. Is that correct?
Correct.
Yeah.
So you're not going to take from them, you're going to share with them.
Yes.
Okay. let's see. Sorry, I'm getting information. So in that case, this is the same thing that's going to happen here with the electron, right? So nonmetals and metals, when they're going to come together, like two parts of town. So you're going to take away from this guy, but you're going to share. So if you have two nonmetals together, you're going to share with that person, right? So nonmetals are going to be sharing. They're going to form covalent bonds with nonmetals. And then if you have a metal and a nonmetal coming together, they're going to be ionic, right? So metal, nonmetal form ionic bonds. Two nonmetals are going to form a covalent bond. You guys get that?
You say two nonmetals?
Two nonmetals. So I'll give you an example, and you tell me if you understand. So phosphorus and chlorine. Are they going to form a covalent bond or a covalent bond or a ionic bond?
Phosphorus and chlorine.
Bond.
A covalent bond.
A covalent bond. Okay.
Yeah.
What about calcium and carbon?
Carbon.
Ionic bond.
Ionic.
Ionic.
Okay. What about carbon and oxygen?
Covalent.
Covalent.
Okay. So covalent bonds are what? What is the definition of a covalent bond?
Nonmetals.
They share.
Sharing.
Electron.
Okay. And then definition of an ionic?
They share.
Are they sharing?
No,
Or is it give and take?
it's either give and take.
Okay. Yes. So ionic is going to be give and take, and covalent is sharing. So that's the basic. Okay. So let's go back to our Lewis dot structure. So we have two fluorines. They're going to be sharing.
Yes.
So if you're sharing, your goal is to get to your octet, to have 8 electrons around you, to be like a noble gas, to be stable. Okay. So the only way that you can do that here is by forming a single bond. You guys see that?
Yes.
That's 2, 4, 6, 8 around this fluorine. 2, 4, 6, 8 around this fluorine. Okay, so that's pretty easy.
Yes.
Straightforward. What about this guy? Nitrogen.
Nitrogen.
How many valence electrons does nitrogen have?
5.
Okay, that's 1, that's 2, that's 3, that's 4, that's 5.
So you count backward, Dr. Henry. 1, 2, 3, 4, 5.
Okay, so can we get this guy to its octet?
Yeah.
So that each nitrogen has 8 around it.
No.
They have 5, yeah.
Well, we can't do it if we have a single bond, but what if we share 4 electrons? Can we do it then?
Yes.
So let's see if we form 4 electrons. So we put 2 here. So total, this has 5 electrons around it, 5 electrons around it. So if we have 2 that are being shared, so that'll be 4, right? So this is a total of 10 electrons that we're working with. Is that correct?
Yes.
Yes.
Okay, 4, and then, so that would be 8. I mean, this will be 8. So that would be 10. So that's 2, 4, 6, 8, 10. So does this guy have 8 around it?
No.
No.
No. So that doesn't work. Okay. So what about if we share 6? So let's take one of these guys and we'll put it over here. So that's triple bond. And we'll erase it.
Then
so that we
yes,
can see
they
it.
would.
Okay, so let's count total electrons. That's 2, 4, 6, 8, 10. So that's 10 electrons total. Okay, so let's look around this nitrogen. How many do we have around it?
2.
So there's 2, that's 4, that's 6, that's 8. Because remember, each line represents
2
shared electrons. So we count that as our 8. And what about this oxygen? I mean, this nitrogen?
The
Also
same.
8.
8. So I'm going to make it a little bit easier to see with a a longer line, so it's a little clearer. Okay. Okay, so you guys see that?
Yes.
Okay, so Matt asked this question earlier. Can they share more than just 2 electrons? So the answer is
Okay.
yes.
Yes.
Okay, what about oxygen? How many valence electrons does oxygen have?
6.
Okay, so
Dr. Henry, so your goal is to get the octet rule with both of them?
yeah, you want to try to get, so right now, until we get to the exceptions, there will be exceptions, you want to try to get the octet rule to obey all of them. That's the first goal. And if you can't get it to obey all of them, you want to get the one that has the higher electron affinity. And we'll talk about how to determine which one has a higher electron affinity. There's a couple of ways of doing it. I'll give you the classic way, and then I'll give you the computational way.
Okay.
How you would calculate. Okay. So we have 6 and 6. I want you guys to work on this for a second. And then we'll start doing ones that aren't even. Okay, do you got some answers?
Yes.
So there's multiple ways to write this, correct, Dr. Henry? Like there's not one right way?
No, there's really one right way.
Okay.
So how many electrons do we have total?
6.
5, 6.
All together. If we're
Well,
Wow.
going to be working with 12 electrons. That's what you're telling me. Okay. Okay, so we have our O. So if we use a single bond, let's say we take one from each side, we'll take one from here and one from here, right? So we have 1. Does that meet the octet rule?
Yes.
It does?
No.
No.
Count. We have 1 electron here. So that's 1. That's 5. That's 7.
Oh no.
No.
Has to be on pair.
So well, I could actually just take 2 of them from this one side and put it there and just put the other one here. Does that meet the octet rule? We'll erase this one. Oops. So that's 2, 4, 6, 8. This one has 8 around it. This one has 2, 4, 6. Does that work?
Yeah.
No.
Nope.
Not even.
Okay, so neither of those work. Okay, so darn it. Back to the drawing board. So what if I take, we'll take 2 from each one. Okay, come on. So I'll take, we'll share 2 from each one. So does that reach the octet rule?
Yes.
Yes.
Okay, so that's 2, 4, 6, 8, 2, 4, 6, 8.
Yeah.
They both have 8 around it.
Mhm.
So that's a go. So that's what it's going to look like. Now you're going to ask me, and I know you are, Dr. Henry, so do I always have to put it like 2 at the top and 2 at the bottom, or 2 at the top or 2 at the side? The answer is no. Right? You could have done it like this. It means exactly the same thing.
So Dr. Henry, I've got a question. Why can't you just write the answer almost the way it is in the product? Like, why can't you just put 0, 1 bond, or excuse me, O, 1 bond O, and then put 2, 4, 6 around each side, and then use that bond in the middle as your 2 electrons?
Because 1 bond in the middle does not count as 4 electrons. This is saying you're sharing 4 electrons. You
So why
understand?
can't you just do a single?
Because it doesn't work out, right? So we tried that earlier. Count the electrons around it. So we tried to do this earlier.
But in the beginning, you've got 2 dots on the left side of this first 0. You've got 5 right now, but at first you had 6, right?
I had 6 on one side. When I did it the other time, you could have 6 on one side. That means you have 4 on the other side. So how many total electrons do we have to work with? Again, 6 plus 6 is what?
12.
Okay, so that's 2, 4, 6, 8, 10, 12, right? You have to have the same number of electrons that you have to work with. You can't just put another set here, because how many is that?
Oh, okay.
Do you understand? So that's what you're asking me? Count how many this
Yeah.
is. So that's 2, 4, 6, 8, 10, 12, 14. We don't have 14 electrons. We only have 12. So you can
Okay.
only work with what you have,
12.
right? Law of
Okay.
conservation, right?
Yes.
You can
Dr.
only
Henry,
use what you have. So that one don't work. Yes.
how about we do 3 line in the middle and do 2 dots and 2 dots inside?
So if we do 3 lines in the middle,
Like the N, we have it on N with the N, you know?
okay, so let's do 2 lines in the middle. And then how many on each side? 2 dots?
Inside. Yeah,
So
2
you're
dots.
saying like this?
Yeah.
Okay, count the number of electrons that we have. That's 2, 4, 6, 8, 10. We have 12 to work with. So again, law of conservation says what you put in, you got to get out. You're getting 2 less. We don't have 2 less.
Okay, Dr.
So that
Henry,
don't
what
work.
about the one that have 5, 5 and a line at the middle?
Okay, so if we had,
Got it. Alright.
okay, so that gives us 12 electrons, but does this obey the octet rule? How many does this guy have around it? So that's 2, 4, 6, 7. Is that 8?
Oh, no.
Nope, so don't work. So we wanted to obey the octet rule and use all of the electrons that we have available. No more, no less. Okay?
Okay.
Simple?
Yes.
Okay. Okay, so this brings us to our next thing, what we call lone pairs. So electrons, they like company, right? So ideally, they would prefer being in pairs because that helps with stability as well too. So
Dr.
these
Henry.
guys are considered lone pairs. So when we draw them, we put 2s together. So these are lone pairs right here, lone pairs. I should put that in a different color, shouldn't I?
You said long what?
Pair. I'll type it out for you.
Okay, no, it's okay. I got it.
Since my handwriting is horrible.
Sure, long pair.
Okay, so those things that are circled in red are your lone pairs. Okay, so you have two lone pairs here, and then you have two lone pairs over here. Okay.
Yes.
Okay. So their general definition is those electrons that are not used for bonding. Okay, so lone pairs are they're pairs of valence electrons that are not used for bonding. Okay. Okay, so we've talked about the Octet rule. Can I clear? Did you guys get everything written down before I move on?
It's long pair, ON, long pair. Long pair not used for bonding.
Okay, so lone pairs, it tells you the definition. So they're valence electrons that are not used for bonding. Makes sense, right? There's two that are not involved in the sharing of electrons. And then the octet rule, right? So the octet rule is just having it surrounded by 8 electrons. So you want to make sure that you have each of the elements need to be surrounded by 8 electrons, a total of 8 electrons. Okay? How you feeling so far? Brain's is it exploding yet?
Kind of.
Excellent. That means we're doing good then. If it's just kind of, it hasn't blown up, we're doing great. Okay, so we've talked about polar versus nonpolar. So we said polar was that uneven sharing, right?
Yeah.
So, and then you have what we call a positive and negative pole. So those are your positive, your partial positive and your partial negative. Okay. So, and then nonpolar is when you have even sharing. Okay, so they're sharing even, they're really close to even. Okay, so these are example of nonpolar, so even sharing. This is an example of polar. So you guys, to kind of explain it as, here's Y, it's bigger than X. X here are equal, so they're the same size. And then ionic is when you just transfer the electrons completely. Okay, so are you guys ready for electron affinity and electronegativity? Okay. So electronegativity is it's basically the ability of an electron to attract your bonding electron pair to itself. Okay, so the ones that are being shared, they're being pulled more towards the bigger one in this case. So these electrons that are shared between these two, this guy gets it most of the time, the little guy gets it a little bit of the time. Okay, so it's the ability to pull those electrons closer to itself so that it gets it majority of the time. Okay, so this basically tells you the schematic, and I'm just going to show you the figure so you can see it, and you can see it a lot better. Okay, so you can go back to it, the text. Okay, so as we go from left to right, our electronegativity increases. As we go from top to bottom, our electronegativity decreases.
Yes.
Okay, so fluorine, because it's only one away from being a noble gas and it's really small, it's like that. Have you ever met that little bully? I mean, he just has so much to prove in life because he's tiny and everything like that. And he fights all the time. So he always has to beat up the biggest guy and everything like that.
Yeah.
Okay, so that's fluorine, right? Everybody has had a fluorine in their life. They're just like mad at the whole world. Biggest bully ever. So, and they're the smallest person, the teeniest person, but they're the biggest bully, you know? So fluorine is gonna take electrons. It wants to take it if it can take it. But since they're in the same block and they know there's gonna be issues, it's gonna share with the nonmetals. So all nonmetals it'll share with, but it'll pull it closer to itself the majority of the time. So the way we determine whether things are going to be electronegative or more electronegative or less electronegative, whether it's going to want to share more so than anything or share evenly, is based upon our electronegativity. So these are arbitrary numbers. Fluorine, since it's the highest, gets a 4. That's the highest it can be, right? So fluorine has the highest electronegativity out of everyone. Look on that, on our little table there. Can you guys see that?
Oh, are you making them or someone?
Yes, I see.
Okay. So fluorine, if it's going to be sharing with carbon, carbon has a 2.6, fluorine has a 4.0. Okay. So fluorine is going to be much stronger than carbon, so the electron is going to spend more time with fluorine than it does spend with carbon. Okay. So the way you determine whether a bond between two atoms, so we're saying C and F, a bond between C and F, where the electron is going to spend more time towards is by looking at their numbers. So fluorine has a 4.
Fluorine.
And carbon has what?
2.6.
2.6. So if you subtract the smaller number from it, that'll give you a range. And so we have a system kind of set up. So, and let's see if we have it. I don't include it. I need to include that. So if it's typically, let's see, what is that, 1.2?
Yeah.
Okay. So if it's less than 0.8, well, actually it's less than 0.6, the difference between the two, if it's less than 0.6, then it's considered pretty much even sharing, right? So like for instance, carbon and hydrogen. What is that value?
Well, hydrogen is 2.2 and carbon is 2.6. So it
Okay.
is be a
So
0.4?
then, so 2.6 minus 2.2 is
Be
what?
0.4?
0.4.
0.4?
Correct. Yeah.
Okay. So is that less than 0.6?
Yes.
Okay. So if it's less than 0.6, it's going to be even sharing.
Okay.
Oops. Now, again, these are arbitrary numbers, and the table is pretty much consistent, but different textbooks explain it different ways, and you'll see that.
2.2.
So if it's less than, choose a different color for one.
If it's greater than 0.6, Dr. Henry, it would be considered non-even sharing.
Okay, yeah, so if it's greater than 0.6, that would be uneven sharing, right? Sharing up till a certain point, right? Because then we get into our metals, right? So we know that we get, let's see. Okay, so we have one point. So I think it's about point. So I think think it's about 1.6. I have to look it up exactly. So if we go from 0.6 to about 1.6, so then it's considered to be uneven. Sorry. And then anything above 0.6,
It's even.
nope, is ionic. Anything above 1.6.
Oh. About greater than 0.6 and even 7.
Okay. Okay, so I have to look at this number to be sure, but ballpark, that's about it, okay? So all you're gonna do is take the difference. So you're gonna take the difference between the two elements you're looking at. And then you're gonna look to see whether or not it's ionic. So this is how you calculate it. Now, how you would do it just by looking at it, right? So the ones that are gonna be closest to the noble gases, they typically have stronger pools than the ones that are a little away. Like, for instance, fluorine is greater than oxygen. Fluorine is greater than nitrogen. Oxygen is greater than nitrogen, okay? So now, but when we look at oxygen and chlorine, well, oxygen is stronger than chlorine because chlorine goes down one step, okay? You guys see that?
Yes.
Yep.
Okay, so you guys are going to have this available. So if you just kind of look at those numbers, it gives you an idea, are you going to be sharing evenly or unevenly, right? So here, these guys are going to be pretty much even in terms of sharing, right? Where these guys aren't going to be even. Okay? So,
Yes. Dr. Henry,
yes,
where we can get that? If that is going to be in the test?
it'll be provided.
Okay.
It'll probably be in that question if it's asked. The
Oh,
values
okay.
are going to be provided in the, okay?
Okay.
What?
But it won't be on this test anyway, so.
Okay.
Ah,
the next test.
oh.
Okay, piece of cake so far?
Yes.
And this basically just shows you that, so shows you what we just talked about. So hydrogen and oxygen. Is that going to be polar or non-polar?
Oh, gotcha.
Polar.
That'll be
Okay. What
Polar.
about carbon and hydrogen?
Still polar.
Carbon and hydrogen, polar? Are you sure?
Carbon and hydrogen.
It's less than, so that isn't it considered even sharing, Dr. Henry?
It's considered even sharing, which is polar or non-polar.
Polar?
Polar is even sharing?
No, polar, it's non-polar. Non-polar
That's
is,
right, it's non-polar, yes. So this would be non-polar, this would be polar.
Yeah.
Okay, we've talked about single bonds, we've talked about double bonds, we've talked about triple bonds. A single bond is when you only share between two pairs of electrons, that's 2 electrons. A double bond is sharing between 2 pairs of electrons, or 4 electrons total. And a triple bond is the case where we're sharing between 6 electrons total, or 3 pairs of electrons, right? So our examples were, we had fluorine, we had oxygen, and we had nitrogen. Can you guys see my dots in all of those?
Yes.
Okay. Piece of cake?
Yes.
Okay.
So we'll never have anything above a triple bond, Dr. Henry?
So technically you can have one where you're sharing all four. You could have this, but it's unstable. It's so rigid, it's not very flexible enough to actually get the sharing to occur. So
Okay.
that's the only possibility, but it doesn't truly exist because it always ends up breaking down. So.
Okay. Thank
Okay.
you.
So yes, triple bond is typically the highest you get. Okay, so you already know that you could have more than one thing attached to an atom. So this is a case where we have hydrogen, right? So this shows you water. So, and this is ammonia. You see that lone pair. So that's 2, 4, 6, 8 around the nitrogen, and then you only have 2 around the hydrogens. That's always very, very important to remember. Now we need to talk about center atoms, since we're now that we know that we could have more than one thing attached to another atom, right? So oxygen is our center atom here, right? The way you usually determine your center atoms, there's 2 ways. If you have hydrogen, hydrogen is always going to form a single bond. It will never form multiple bonds. It can only form one bond. So you will never have hydrogen in the middle. So you're never going to see something like this. Because that has 2, 4. That would be 4 around hydrogen. That will never happen because that's well above its octet. It can only hold 2. So this will never happen. Never, ever. Okay? So you will never have hydrogen in the middle. Okay? So anytime that you have a molecule with hydrogen, you know that other atom has to go in the middle. So let's say we have something like this. Who's going in the middle?
Carbon?
Carbon.
Carbon.
Okay, so this one is an easy one. This is called methane. We've talked about it before. Where's it found? Primarily in the valley. Where do we get most of our methane from?
Cows.
Cows. Okay. So you know immediately, as soon as there's hydrogen, you will never have a hydrogen in the middle. You don't know how many times I've said that and how many times I've seen them on test. Okay, so ideally, there are some exceptions, but for the most part, when you draw your Lewis dot structure for a molecule, a covalent molecule, it typically forms like quads or 4 things around it, or 3 things around it, or 2 things around it, right? You typically don't have anything like this. Well, that isn't true until you get into organic chemistry. So let's see. You're not going to see something like this. Okay, why doesn't this work?
Well, would it be because there's more than 2 bonds attached to hydrogen? So it breaks the rule of having only 2, is it 2 molecules attached?
Yeah, so it breaks the rule there's two bonds here, right? It breaks the octet rule for for hydrogen, right? Because hydrogen can only have 2 electrons around it. That's 2, 4. We have 4 around this one. So we know that this can't be right immediately. As soon as you see that, you're wrong, okay? So if you have a chain of hydrogens together, you're wrong. That doesn't work, okay? So you know that it has to be an end, right? It has to be at an end. Hydrogen always has to be an end because it can only have a single bond. So this works, but this does not work, okay?
Okay.
Okay. So, how you guys feeling so far?
Good.
I like that. That's great. We only have 5 more slides, and then we're finished with chapter 12. And chapter 13 is a piece of cake. So, remember I told you there are exceptions?
Yes.
Okay, are you guys ready for the exceptions?
Yeah.
Yeah.
Okay, good. Okay, so odd number of electrons. So if you count your total number of electrons, so no. What is the total number of valence electrons for nitrogen and oxygen? How many valence electrons does nitrogen have?
5.
Okay, so it has 5. And then oxygen has how many?
6.
It has 6.
It's not even.
That's right. So 5 plus 6 is 11.
11.
So any way that you do this, you can do it 15 million different ways. I usually make a bet on this because I always get free money for this. So because you have an odd number of electrons, there is no way that you can fulfill the octet rule. Never. It can never happen. Okay? Because altogether it adds up to an odd number. There's no way it's going to happen. Okay? So that means you have to figure out the best way of doing it. Both of these molecules exist. They're very reactive because they're kind of unstable, but they do exist. So nitrogen monoxide is going to satisfy the octet rule for oxygen first because oxygen is more electronegative than nitrogen, okay? And then it's going to do its best to make nitrogen happy. But since oxygen is a bigger bully, oxygen is going to make sure that its octet is satisfied first, then nitrogen gets what's left over, okay? And so you see this here, it's satisfied. Oxygen has 2, 4, 6, 8 around it. How many does nitrogen have around it?
7.
7, right? And so that's what's going to happen. The one that has the least electronegativity associated with it is going to get screwed, okay? Think about it's bully theory. That's what we're going to call this, bully theory, right? The bully is going to make sure that it gets its stuff first, and then what's ever left over, the other one gets, okay? So that's the same thing that happens here. 2, 4, 6, 8 around this oxygen, 2, 4, 6, 8 around this oxygen, and count how many is around the nitrogen.
7 as well?
7 as well, right? So both of those got their 8, and then nitrogen gets what left over? It's screwed by 1, right? So do you guys see that?
Yes.
Okay. So another way that we get screwed here is when we have, this is called hypervalent, right? So count how many bonds are around the phosphorus and the sulfur here. Or how many electrons are around the phosphorus?
10.
10.
10. So that's 2, 4, 6, 8, 10. Does that obey the octet rule?
No.
No. Now look who is it interacting with.
Fluorine?
Oh, the bully guy.
The bully guy, that's right. Fluorine, the biggest bully. So fluorine bends things to its will, right? So since since phosphorus, if you look where phosphorus is on your periodic table, phosphorus is in the 3 orbital in the 3rd period, right? Is it not?
Yes.
Okay. So since it's in the 3rd period, it actually has access to the 3D orbital. So it will adjust itself only because of phosphorus. I mean, because of fluorine, because of the F, right? Only because of the fluorine, it will adjust itself so that it can use that 3D orbital to sit there and put more electrons into itself, right? And so it disobeys the octet rule because it will use the 3D orbital to sit there and put electrons in, or the 3D subshell to put electrons in. And that's only because it's pairing up with this noble gas who's a really big bully. It does it with some of the other ones too, but fluorine, you'll notice fluorine will do this to a lot of elements. So like, look at what it does to sulfur. Exact same thing. Because it can use the 3D orbital, it'll actually be hypovalent. Okay, you guys know that second part of it, I'm giving you more information, but it's the truth. It's because it has that 3D orbital that it can do that. But these are exceptions. And so you need to be able to recognize these exceptions, okay?
Okay.
So we have odd number of molecules. We have what we call hypervalence. And then we have hypovalence, right? So again, look who's involved in this.
Fluorine.
Fluorine. So yeah, fluorine, he causes problems, okay? And because he causes problems, you know, if you look at beryllium is a metal, you would assume that he would just take from it. But fluorine will cause issues like this every once in a while. It won't take away completely. It'll say, okay, we're going to share. We're going to share on my terms, okay? And so he did the same thing with boron here. Boron doesn't have 8 around it. It only has 3 around it. Beryllium only has 2 around it, right? I mean, total 4 electrons around it, okay? So this, again, is hypovalence. Hypervalence and hypovalence. Do you want me to type that out?
Please.
Please.
Yes.
That's hypovalence. And then the other slide. Oops. This one is hyper. Hyper, if you think about somebody who's overly excited, so more. Okay, so hyper, hypervalence, and then hypo. Clear. Okay. And then occasionally oxygen will give us a little complications as well, but it's rare, you know. Here. Okay. Okay, so the last type of bond is called a metallic bond. I skipped the slide, hold on. Last type of bond, yeah, okay, we're good. Last type of bond is a metallic bond. So a metallic bond does something kind of funky too, right? So what it does, it'll actually delocalize an electron. So it'll kind of like just drop the electron next to it and pretend like it's not there. Like, you know, have you seen somebody drop a napkin or something and pretend like it's not theirs or something like that?
Yep.
Okay, so that's what it does with an electron. It'll just drop it there and like, oh, that's mine. And so you'll have electrons next to the positive charge. So if sodium drops its 1 electron that it needs to get rid of, then it's positive and that electron is negative on its own. So it'll look something like this. Oops. Okay, so that would be like your sodium molecule, that's the electron. That's your sodium molecule, that's an electron. So this is considered to be a metallic bond. So it's using that electron to sit there and get that plus and negative charge so they're able to interact. It allows it to be stable for a while until something comes along better, right? And then this is the case of like sodium. This is the case of like magnesium, okay? You guys see that?
Yes.
Okay. So Now, this is also how alloys are made, right? So you could have two metals coming together, and since two metals they're interacting and they're mixed, they'll be mixed in solution. So basically, we could have, like, say, sodium and lithium, right? So this guy will be a lithium, that'll be a sodium, right? And so all it is will be a little bit bigger, but they're going to be interacting because of the delocalized electrons, okay? And so we use alloys for tons and tons of things. How many of you guys like bling, jewelry?
Oh yeah.
Who's got a rose gold ring?
Yeah.
Okay. How many of you guys got 14 karat gold?
Yeah.
18 karat gold?
Yeah.
You've heard of brass?
Yes.
You notice brass is not on the periodic table? Because brass is an alloy, okay? So it's a mixture between metals. So these are some examples of some of those alloys, and you can look it up. Rose-colored gold is just another alloy, right? And that's what gives it its color, because you have a mixture of different metals in there. And so those are made by metallic bonds. So a metallic bond is just a bond or interactions between metals, okay? And it's just that delocalization of the electrons that allows those metals to interact with each other or to bond together. Okay? Piece of cake?
No.
Who said no? Andy?
That's me.
Okay.
Andy.
So Andy, so all I'm saying is that all alloys are two different metals that are bonded together by using a metallic bond. And so if you have two metals coming together, it's going to form a metallic bond. It's not going to be an ionic bond. And all it's going to do is delocalize its electrons, if I can get there. So it's going to drop that electron so it has the charge that it wants. So it'll drop it next to it so it gets that charge. And then the other metal is also going to do the same thing. And so they're using the electrons to keep it together. So they're still forming that interaction, that positive and negative, but they just delocalize. They let go of that electron so that they can use that positive and negative type of thing so that they can be like noble gases. Okay?
Okay.
Okay,
Jump.
questions, concerns, Cash.
Gosh.
This is the first time that we finished a complete lecture. Are you feeling good?
Yep.
I'm hungry.
You say you're feeling great? That's even better. Yeah, get that stretch. Tap yourself on the back, making progress.